Okay, folks, we've already mentioned that resistance is futile. Yes, we have. We talked about Ohm's law, and the ohm is the unit for resistance. You know, the upside-down horseshoe that you make awesome people out of, like Obama, Tom Cruise. I just keep coming up with them. That's awesome. Now, this is an equation for resistance. We can get it. We can calculate resistance by using the resistance equation. Now, the resistance equation has, you can see three things in it. Okay, three things, and those three things are as follows. And if you think about it, you kind of know this should be true. This should make sense. Actually, before we dive into it, think about it. Wires aren't all created equal. Some wires are very little thin ones, and so thin, thick. I always say that wires are like the roads for electricity. Think about it. If you are driving down a highway that's 4 lanes, okay, and you've got 100 cars that are driving on the 4-lane highway within a mile. Now, if you have a 1-lane highway and you have 100 cars driving on that 1-lane highway within a mile, whoa, it's going to not be moving very fast, is it? Because, not a lot of lanes will allow the flowage. And especially, it's like going out to Route 101, heading out to Keene on a Sunday afternoon and get caught behind Grandpa. All right, and Grandpa decides to go 30 and a 50, you're stuck because Grandpa's dictating the rate of flow because you can't pass. Same thing happens with wires, okay? Electrons are like little cars on those highways, the wires. You with me on my analogy? Pretty good analogy. Yeah, you're welcome. Okay, so now those electrons, if it's just a thin wire, they can't get by each other. They're bumping into each other. They're cars without brakes is what they are. They don't have any brakes. But if you have a wide wire, those electrons can more room. So the wider the wire, the blank, the resistance. The lower, yes. So wide wire, low resistance. Thin wire, higher resistance. And that's why you have thin wires. The filaments are thin wires. They have a lot of resistance and cause all those little electrons, the cars without any brakes, to crash into each other and cause all that heat and generate that sweet light that we all love. Okay, now, what about the length of the wire? Okay, the length of the wire is going to make a difference. If it's a shorter wire, or a longer wire, okay, that's going to make a difference in terms of the resistance. The more wire you have to go through, the more resistance you're going to encounter. I think that would kind of make sense, right? If it's a long wire, there's a lot of resistance that builds up. So the longer wires cause more resistance, short wires cause little resistance. Okay, well, what else? And by the way, now we can go to the equation. Now, at least we've actually got 2 of these already talked about. Yes, we do. Because in the resistance equation, we have the length of the wire. So the longer the wire, that's my little L. That's what that means. That means the length of the wire. So this would be in meters, length of wire in meters. And so this is directly related to resistance. So the more length of wire, the higher the resistance, direct relationship. Now, down here, A is area. That's the area. Like the area, wires are generally, they're elongated. They're circles. They're like tubes filled with all kinds of metal goodness. And so those are circular. Cross-section of a wire is going to be a circle. So the area, okay, that the electricity can go through. The larger the area, big area, big number in the bottom, big number in the denominator. Come on, resistance decreases. Yes, it does. And if you have a very tiny little wire, just like a cute little wire, if a small wire with a very small resistance, you have a very small number on the bottom, the resistance goes way up. So there we go. Okay? Okay? Big area, low resistance. Longer wire, more resistance. What's this? What's this thing here? That looks like the Greek letter rho. Very good, Billy. You know your Greek letters. Yeah, I do. Okay, Billy, that's awesome. Now, this is the Greek letter rho. And sometimes you'll see it in physics. It's used for density as well. Sometimes that happens. Physics will use various Greek letters in multiple different times. I don't know. It's confusing. Whatever. But anyways, what it means is the resistivity. I thought that was resistance. No, this is resistance. Resistance has to do with length of wire, thickness of wire, and the resistivity of the material that the wire is made out of. Some things have more resistivity than others. Some things have less resistivity. Okay, all right. So like most wires are made out of copper. Not all. Some are made out of aluminum. You can make wires out of gold if you wanted to. They're really expensive wires, but you can do that. And so different metals have different resistivity. Some are more resistant than others. Copper's resistivity is relatively low. All right. Yeah. Aluminum is a little bit higher, if I remember right. Gold is low, but you know you have different reasons. So there are tables for the figure to find these things. You would find the resistances in tables in physics books when it comes to resistance in circuit units. So you would find them on Zoom tables. Of course, you could always look them up. Any metal has a particular resistivity associated with it. Well, the higher the resistivity, that means the more resistance it's going to apply because it's a direct relationship. So this has to do with the material, We're usually talking about metal here. How high is the resistivity of the metal you're using in the wire? Okay, all right. High resistivity, high resistance. Low resistivity, low resistance. Okay, those are the things that we can talk about. Oh, there's one more thing that's not actually in the equation, and this is just in general. I almost forgot to mention this, is that temperature makes a difference. Temperature actually makes a difference in resistance. When wires get warm, they get hot, okay, then what happens to their kinetic energy? Well, let's see, kinetic energy, I remember that. That was the temperature unit. Yeah, kinetic energy is directly related to temperature, correct. So if we have high temperatures, because, electricity's been moving along and electrons don't have any brakes on, they smash into each other, the temperature increases, and that causes the kinetic energy to increase, so the particles are moving faster and faster and faster. Now, so if temperature goes up, kinetic energy goes up. If kinetic energy goes up, the particles are moving faster and faster and faster, vibrating at a faster rate, making it more difficult for electrons to move through the wire itself. So it's all about free-flowing electrons trying to move along that wire. And those free-flowing electrons, if you've got particles that are all excited because they're such a high temperature, it's going to be really hard for those electrons to get through. Lots of collisions, slowing them down. So that means that the higher the temperature, the higher the resistance. The more those excited, vibrating, high kinetic energy particles, because of high temperature, are going to cause the free-flowing electrons trying to get through a difficult time to do that. All right, so that's the other one. That's the fourth one. So I was trying to remember I knew there's four of them. I said, wait a minute, I'm going to go on for three. Okay, so here they are. Width of the wire, length of the wire, what the material is, and what the temperature is. If this is high, resistance goes up. If it's low, resistance goes down. Superconductivity, you might have heard of that before. Superconductors. Superconductors are created when you have in very low temperatures. In very low temperatures, wires have hardly any vibratory motion inside, and you can zip things right through those wires. Superconductor. Okay, cold temperatures. All right, I think we're going to wrap this up. That's what I'm talking about. This is the equation we need to know for resistance, and those are the things that go into determining the resistance of a wire.